Hello everybody, my name is Muhammad Ahmed and I am PhD student at the University of Buckingham. We work on the improving generalization of ENAS-based CNN models for breast lesion classification from ultrasound image. So CNN architecture have been extensively used in all application areas in image classification, including medical image classification. In general, there are two main ways for designing CNN architecture. The first way is handcrafted CNN architecture, which is used for designing so many state-of-the-art, for example, VGGNet, ResNet, DesNet. And also designing a CNN architecture requires more knowledge and time consuming manually. For solving this problem, there's recently developed architecture which is automatically designing CNN architecture, and the most common as NAS, and the efficient one is ENAS. But the aim of these two ways is designing successful and robust CNN architecture, which is perform well also on unseen dataset, not only in the internal dataset. So ENAS microsearch use it for optimizing CNN architecture for breast cancer classification, and microsearch consists of two stages. The first stage, controller designing or searching for optimal pair of cell, which is normal cell and reduction cell. Then we stack these cells together to get the final architecture in the second stage. Then we train the final architecture on our data set from scratch. Then we design it ENAS-17 and trained on our balanced data set from scratch. Then we compared with the existing technique, which is these AlexNet and CNN3, also trained from scratch on our data set. And we found that our ENAS-17 it's outperformed both in terms of accuracy and the other measurement. Then this work published in MIUA2021 entitled an ENAS-based approach for constructing deep learning model for breast cancer recognition from ultrasound image. But our goal is to design a model which is perform well also on unseen dataset, and the ENAS might more likely to overfit because they are using the same data set for searching and for the modeling. Because of that, we prepared another set of external data set and we test our ENAS-17 on it to see the generalization rate of our ENAS. So for that purpose, we prepared a new data set to be used as an external data set, and also we have another data set to use it as a modeling part for solving the problem of overfitting of ENAS-17. So the two data sets, which is a pushy data set and Tandy data set, are using as an external and unseen data set for evaluating ENAS-17. And bushy dataset is came from different sources, which is publicly available, and Tandy dataset and modeling dataset provided for us by our collaborator Tandy Innovation. Okay, now time to see the performance of our ENAS-17 on unseen dataset. Then we use it both bushy and Tandy test dataset and test it on our ENAS-17. Then we found that there's a huge amount of reduction on especially in true negative rate, which is more than 20%, and also we have 10% in a drop of accuracy. This is meaning that we have a generalization error in ENAS-17. Then we want to solve it. So to solving this problem, we thought about different technique of solving the overfitting and of CNN model. So for reducing the generalization error of in our ENAS-17, we examined different approaches. And we listed all the approach of reducing the overfitting, and some of them which currently exist in use it in ENAS-17, which is dropout and batch normalization and regularization. Because of that, we didn't do more with these, but we start from reducing the complexity, and also we do use it data augmentation in different scenario, and also we proposed a new and a different way of solving the problem, which is unbalanced dataset, because we found that our model mostly sensitive to true positive rate. That's why we want to increase the number of benign case and solve that problem. So first of all, we thought about reducing the complexity, because one of the reason of happening the overfitting is overparameterized. That's why we reduce the number of the layers from 70 to 7. We didn't change any other hyperparameters from the architecture. Even the cell, we used the same optimal cell that generated for ENAS-17, and we used the same dataset for trained from scratch ENAS-7. Then we found that still we have the same or close amount of the reduction, and this is showing that there is no over parameterized issue with ENAS-17. Then the second approach is using data augmentation in different scenarios to find the effect of data augmentation on ENAS-17 overfitting. So at the first, we will show the method that we use it for data augmentation. We use the rotation and mirror and SVD. And also the scenario was like that. The first, we trained ENAS-17 only on the original region of interest. Then we used all data augmentation, and then we group it by SVD and mirror, then rotation and mirror, and we trained ENAS-17 on each one of these. Then we found that still we have the same amount of dropping on true negative rate and accuracy. And then this is showing that still we have the problem of overfitting in ENAS-17. So even with applying the different approach for reducing the generalization error of our ENAS models, we still have this reduction in true negative rate. That's why we thought about increasing number of benign, because we thought that it might be some of the features of benign case will be loose during the training strategy. That's why we use a different ratio until we find that the optimal ratio, it was 1.93, which was almost the number of benign case, double of number of malignant in our dataset. Then we use this dataset to train our ENAS-7 and 17, and the results show that there's an improvement. So after training and ENAS-7 and 17 on unbalanced dataset, we will show the result or impact of the unbalanced dataset approach on improving the performance of our ENAS models on external dataset in this slide. So the first, if you look at this graph, then you will see that there's improvement in term of accuracy comparing to the internal test and comparing to the previous approach that we showed in the previous slides. Then also the true negative rate, if you look that there's a drop only 9% in each on each dataset, even for ENAS-7, while in the previous approach there was more than 20% dropping. This shows that our approach or unbalanced approach, it is a most effective approach for solving the problem of overfitting or generalization error for our ENAS models for breast cancer classification. Then to see is ENAS worse in overfitting than other architecture, we compared ENAS with other existing technique, and we used 3 for transfer learning and 1 from scratch, and the results show that still ENAS-7 and 17 outperform the existing technique on balanced data. And also we did the same comparison. We are using unbalanced dataset, and for unbalanced dataset we found that our ENAS models, it's outperformed the others in terms of performing on external dataset, and also there's a balance between true negative and true positive rate in ENAS models. In conclusion, we investigated the effect of ENAS approach for design, CNN architecture for breast cancer classification from ultrasound image, and also we investigated unbalanced strategy for reducing generalization error in ENAS-17 and ENAS-7 models. For future work, we will plan to modify ENAS architecture in terms of operations using insert space and backbone structure.